Hello everyone, my name is Alvin Brandon from the Department of Computer Science, Makerere University. Together with my teammate, Wanira Benedict Okelo, and under the supervision of Dr. Marvin Galiwango, we present our project titled Graph Reasoning Vision Models for Real-Time Risk Valuation and Incentive-Based Sorting. So this project explores how advanced AI, particularly large vision models and graph neural networks, can build smarter, cleaner, and more rewarding waste management systems. So here's a quick look at what I'll be presenting today. I'll begin with the introduction, then move through related work, problem statement, objectives, contribution, methodology, dataset and EDA, model results, conclusions, and finally, our next steps. So many waste management systems, especially in developing countries, still rely on manual sorting and basic image classification. These methods fail to handle obvious types and often lack incentive mechanisms to motivate recycling. And our work addresses this by combining graph-based reasoning with AI-driven incentives, allowing AI not to just classify waste, but to also understand it and reward users for sorting it correctly. Globally, AI has been applied to smart recycling, waste sorting robots, and predictive waste collection systems. However, as this chart shows, local adoption remains very low. Most waste collection here is still manual and mostly paper-based. The systems we currently have focus on mostly collection logistics, not classification or insight. Our research aims to change that by combining real-time classification, prediction, and behavioral motivation. And so the left side of this slide highlights domain-level problems such as poor sorting at source, lack of incentives, and health risks from improper disposal. On the right side, you can see the computational problems we address. For example, multi-class waste image classification using GNNs and live vision models, overfitting and low per category accuracy in baseline models, forecasting waste volumes using time series models and GANs, and also graph-based reasoning for incentives. Together, these challenges define the technical backbone of what we have going on here. So, members, our research was guided by four major questions. The first one being, how can AI models improve automated waste classification? Secondly, what forecasting techniques can accurately predict this? Thirdly, how can AI-based incentives motivate communities to sort waste correctly? And lastly, can GANs or hybrid models enhance waste anticipation visually and quantitatively? And these questions were paired with a few objectives, such as comparing CNN and LVM performance, building forecasting systems, and evaluating AI-driven methods against traditional ones. So our main contributions are, we've developed an AI-based waste classifier using CNN and vision transformer models, building an ensemble model to boost accuracy and generalization, a forecasting pipeline using Prophet, CNN regression, and GANs, and lastly, introducing a comparative evaluation framework for real-world testing. Let's look at our methodology and system architecture. So this is how our system works from start to finish. Waste images are captured and processed by a large vision for classification. If the waste is recyclable, it's linked to an incentive system that rewards the user. If it's not, it passes through a graphic zoning module for deeper analysis. The system also uses GANs to generate synthetic images for model training and profit for forecasting waste patterns. Finally, it integrates the Google Maps APIs, optimize collection rates, creating a fully intelligent waste management workflow. Um, for our dataset, we used the real waste dataset from the UCI machine learning repository, which includes over 4,000 images across categories like plastics, food, glass, metals, paper, and also vegetation. So as shown here, the dataset is well distributed across all waste types, preventing model bias. The sample images also display good variation in lighting, color, and texture, which is ideal for robust model training. However, some categories visually overlap, such as shiny plastics, which tend to resemble glass, or contaminated paper, which at times seems like organic waste. So these insights from the EDA guided our data augmentation using GANs, helping to improve classification for difficult or overlapping waste categories. So let's talk about our GAN model. So the Generative Adversarial Network enhances our dataset through image generation. The generator creates synthetic waste images, while the discriminator learns to tell what's real from what's fake. If the discriminator gives a score of above, I think 0.0, the image is accepted as real and passed to the vision transformer. And our graph here shows improved accuracy after our GAN integration, especially for the low frequency waste types. This process effectively balanced our dataset and reduced the effects of overfitting. Next, I'm also going to discuss our vision transformer, and this is its architecture. On the left side, the vision transformer combines CNN feature extraction with transformer blocks. In the center, the CNN layers capture local spatial features such as edges and textures. And on the right hand side, transformer layers then model global relationships between the image regions. And finally, the classification head aggregates these features into a prediction. So this hybrid approach really helps the model to understand not just what an item looks like, but its broader visual context. So let's talk about our knowledge graph or the GNN model. So this slide explains how the graph neural network uses the knowledge graph to enhance reasoning. The GNN starts with visual features extracted from our visual transformer like we noted earlier, with details like color, texture, and shape. Yeah. So all these features are then processed through two main paths. The first one being the visual path, which focuses on raw image data, and the knowledge graph path, which connects the item to related materials using relational graph convolutions or RDCs. So in this graph, each node represents or a waste type. For instance, plastic, metal, or glass, while edges describe relationships such as is recyclable or contains alone. The GNN then fuses the visual and relational data, allowing the system to understand not only how an item looks like, but what it's made of and how it should be handled. For example, a plastic bottle with a metal cap gets linked to both materials and is correctly classified as a mixed recyclable waste. And so about the GNN in summary, the knowledge graph gives our AI context awareness, enabling it to reason about materials and make more accurate classification and incentives. So let's talk about our model selection and deployment. Here's a simple comparison of our models. We used 3 models generated, and our CNN achieved 88.85% accuracy with fast training time. The visual transformer achieved 88.42%, but with better generalization. The large vision model reached 69%, though it had some pending further optimization. Each model has, like we earlier noted, the CNN for lightweight prototypes, the visual transformer for production, and the large vision model for large-scale deployment. So let's take a look at our system metrics and equations. So we use key metrics such as accuracy, precision, recall, and F1 score. So this chart shows steady improvement in generator discriminator losses over training epochs, confirming GAN convergence. Ensemble is also averaging further improved classification consistency across all waste categories. And for our conclusions and limitations, the results we've been able to see show that our vision transformer outperformed the CNN by about 17.77% on average. Graphics improved multi-label classification, and GAN augmentation helped under poor lighting conditions. However, we face challenges such as limited dataset diversity, dependence on camera quality, and mobile hardware constraints, and also reliance on user participation for accurate labeling. And for our next steps, we're really planning to firstly expand our data sets using localized and synthetic data, and maybe implement federated learning for privacy preserving updates, integrate Prophet and Google Maps APIs for predictive routing, launch pilot tests with KCCA and private partners, and lastly, maybe develop a municipal dashboard for city level waste analytics. Lastly, we sincerely thank Dr. Marvin Galiwango for his guidance throughout our project. We also acknowledge the UCI Machine Learning Repository for providing the rule-based dataset, and also my lovely viewers, thank you for your time and attention.